Welcome back. Unit 7, Introduction to Kinetics. Kinetics. The speed of a chemical reaction is also called the rate of reaction, varied dramatically from seconds to years. So what we basically mean here is like some reactions are faster than the others. Some they can just take a second, some they take years to occur. So kinetics is mainly concerned about measuring the rate of reactions. So several factors can influence the rate of reactions. Several factors can influence the reaction rate, and the study of the interplay between these factors and the rate of chemical reaction is called kinetics. So there is what we call activation energy. So activation energy is the minimum amount of energy needed for a chemical reaction to occur. Three important things to note. Here it's not. To note in kinetics are collisions, energy of collision, and orientation of molecules on collision. So these are some of the three things that determine the rate of reaction. So factors affecting reaction rates. There is the physical state of the reactants. Larger surface area leads to faster reactions. So for the example, like if we have small particles compared to big particles. So small particles have got a larger surface area as compared to larger particles. So in fine substance, the rate of reaction will be faster. Then concentration also. The concentration of reaction increases the frequency of collision, which means, let's say you have got two substances with different concentration. So here, we can use a different color. Then here, this will be concentration. Then another one will be very concentrated. So it means, let's say this is A and this is B. So B, because it has got a larger concentration of a certain substance, it creates more collisions. That's what we are trying to increase the frequency of collisions. Then that increases the reaction rate. Then temperature. Temperature at which the reaction occurs, molecules at higher temperatures have more kinetic energy. Ke represents kinetic energy, leading to higher frequency of collision. So what we are basically saying is like, let's say this one, when it's at a higher temperature, it moves faster. It moves faster around the container, as opposed to a lower temperature, it will be maybe moving very slowly. So when the particles inside the container are moving faster, it means the chances or the frequency also of collision is increased. So basically, what we are saying, you can have two containers, let's say A and B, with the same concentration, like this, but the one at a higher temperature, let's say 100 degrees, the reaction will be faster than the one at 10 degrees. So that's why I'm saying temperature at which the reaction occurs, it also affects the rate of reaction. Then the number 4 is the presence of a catalyst. So presence of a catalyst, it reduces the activation energy of a reaction of so the presence it reduces the activation energy of a reaction of increase the local concentration of reactants on the surface. So here there's a bit of a typo error, but basically what we mean here is like remember what we did. Let's say the activation energy is at this level. So if you introduce a catalyst, it can reduce the activation energy to a lower level because the catalyst has come. So it would take less time for the reaction to occur because the activation, the energy that is needed for the reaction to occur is reduced. So the catalyst can reduce the boundary. It's more like a catalyst is like steroids. When you are working out, some people they use steroids for them to develop cuts and six packs faster. So steroids are more like catalysts. They catalyze your muscles to take the shape you want quicker. So that's more like the presence of a catalyst. It reduces the activation energy, which therefore makes the reaction to go quicker than it would normally have done in the absence of the catalyst. So, okay, I was just checking to see. So reaction rates. So reaction rates is calculated as change in concentration divided by change in time. So it's concentration, final concentration minus initial concentration divided by change in time, like final time. Change in time is like start time. You can say T1, end time minus starting time, start time. So basically that's how it is. So these ones we'll cover them at the practice questions when we do the reaction rates. And so reaction rates can be expressed as plus or minus. Positive reaction rates measures the appearance of products, while negative measures the disappearance. So some reactions they make something disappear or dissolve or whatever. Then the other one makes something appear. So it depends. Is it a synthesis reaction? Is it a dissolution? Is it a decomposition reaction? Whatever, like what you discussed when we were dealing with the type of reactions. So, but these things can be understood much better when you are doing practical examples and exam questions. Then you can fully understand. So units of rates of reactions are moles per liter second. Moles per liter second. Rate laws and the rate constant. So the reaction rate is proportional to the concentration of a reactant. If the reaction rate depends on the concentration of two reactants, let's say A and B, it follows that the rate is equals to K, which is the constant, and A and B, which are the reactants, and M and N, which are the reaction orders. This is the rate law. So the rate law is this one. So K is the constant which will be given. Then A and B represent the concentration. And N and B is the reaction orders of A and B. Then the overall order of the reaction is the sum of A and B. So don't struggle and worry about what's the order of a reaction. and whatever. This is just some of the chemical things that have been calculated by scientists, so don't worry much about. So when it's 1, let's say M is equals to 1, we say it's first order. If it's 2, it's second order, and so on. So the rate constant K is dependent on the reaction conditions. Its units are moles per liter per mole per second, which is like, in other words, L over ms, like this. The reaction orders can only be obtained experimentally. That's why I was saying don't have to worry about them. These are calculated by the chemical engineers, chemists, whatever, and do not necessarily correspond to the stoichiometric coefficients in a balanced chemical reaction. So what we basically mean, if you say hydrogen plus oxygen, they combine to form water, like that. Yeah? Like this. So it's now a balanced reaction. 4 hydrogen, 2 oxygen, 2 oxygen. So it's balanced. So when you are referring to the rate law, we are saying the rate is equals to K. Then remember the reactant hydrogen to the power M, and oxygen to the power N. So what we mean is like this M and N, they are not these numbers here. So in this case it's a 1. So you cannot say, so we are saying that's why they do not correspond to the stoichiometric coefficients. So these ones are calculated experimentally. So it means you will be given. So when these rate law and rate constant rate law equations, the rate orders you will be given. So the most common reaction orders are 0, 1, and 2. So 0 order, first order, second order. So 0 order reactions do not depend on the concentration of the reactant. So it means 0 order, they are not influenced, which means the rate of reaction is not increased by increasing the concentration. So it means concentration is independent from the rate of reaction. So this will be regarded as 0 order reactions. So for you to understand this deeply, we need to solve a lot of problems, practical examples, exam preparation. So this will be covered on our website. So if you are interested, please check out our website. For more information, you can use the email on our right. So we are still developing some of the courses there. So it will be online very soon. So thank you so much for watching. And I believe this section, it has given you something. Please like, share, and subscribe to our channel. Please comment below if you are enjoying, so that we can know that it's at least helping somebody out there. Thank you for watching. Have a great day. Bye-bye.